Okay, so today it's about a really cool uh, problem. At least I thought it was really interesting when I first learned about it. It's going to be about counting distinct elements in streams. Let me first invoke the power of cut and paste and remind us what we've done up to this point. We did linear of expectation lecture 1, lecture 2, heavy hitters, introducing hash functions. We did some Markov's inequality. Lecture 3, we did more intense hash functions, more intense higher order moment inequalities, and analyze linear probing. Lecture 4, we did our first graph algorithm. We did a randomized algorithm for minimum cuts. One of the tools that came up was this Galton-Watson process. Lecture 5 was really our introduction to the Chernoff bound, and the example we used was random graphs and how the Chernoff bound leads to this interesting phenomena of always having a giant component in a random graph with average degree at least 1. Last class was about randomized rounding to approximate NP-hard problems. We did maxat and set cover together. We didn't really talk about covering integer programs, but I'll only mention that it sort of takes the ideas from set cover and uses the Chernoff bound instead of some of the direct calculations we did. So that brings us to today's lecture, which is about this distinct elements problem, but some of the tools we'll learn or introduce along the way. It'll be our first encounter, I think, with continuous random variables, which you guys have probably been exposed to before, so it'll be brief. Variance, which is sort of one step up from average, will play a role in today's analysis, and we'll also talk about techniques to reduce the variance of our experiments. Okay, so distinct elements, or let me first say this. Okay, so I don't know, have you guys ever used or heard of Google Analytics? Okay, so websites, if you run a website, you can use Google Analytics. It's some, I think, probably JavaScript thing. But what it does for you is it tracks or it analyzes your web traffic. So somehow Google is collecting the IP addresses. That's what it's doing, and then maybe it can give you some information about demographics or how many people visited and stuff like that. All right, what's the most exciting feature of Google Analytics? If you had a website, what would you want to know? That's true. But give me like something more precise. What's the number one thing you want to know? The simplest thing. The number of users. Okay, so good. So one thing you can say is maybe how many times your website gets visited. Right? That's one. And I learned this because I do host websites. Most of the people who come to your websites are in fact weird bots and they don't really care about you. Okay? They don't want to read your papers. That's what I've learned. So a lot of the traffic is just the same bot over and over and over again. So you're not necessarily interested in how many times your website is visited, but maybe you're interested instead in how many different unique visitors come to your website. Okay. So that's sort of the problem we're interested in today. All right. So here's a web page I found where they describe how Google Analytics and other similar software, presumably, it tries to keep track of the number of distinct visitors to your website, right? Especially given like you're not really supposed to save certain piece of information and stuff like that. Okay, so maybe I want to, great. So maybe I want to highlight just one passage in particular in the second paragraph. So in early 2017, began updating the calculation for users and active users metrics to more efficiently count users with high accuracy and low error rate, typically less than 2%. Okay, so I think there's a couple interesting things going on. One, it was updated as recently as 2017. So this is something that people still work on pretty recently, keep making updates to. Okay, somebody in Google cares about this. Another is that maybe the word efficiently. Okay, so somehow they're focusing on the issue of how to efficiently count users, and they say with high accuracy and low error rate. So they're not promising to count the number of users exactly, right? They're only trying to be accurate and correct most of the time. Okay, so they're using some approximation algorithms. All right, and then I poked around a little more, and I noticed that around 2014 or 2013, some people working inside Google wrote a paper about implementing data structures to count distinct elements. This is about, I guess, some implementation details upon something called hyperlog-log, which is a popular algorithm for distinct elements, a little bit different than what we'll do today, which is a cleaner thing. Okay. All right. So the point is, people do this stuff. All right. So what's the problem for us? So we're going to go back to the streaming model, like lecture 2, like the heavy hitters problem. As before, elements are coming in one at a time at a stream. The stream you want to think as being effectively infinitely large. And you are a relatively small computer processing these elements one at a time. Okay. So in particular, you don't have space to write down all the keys you see. That's the main point. And the question is, how can we estimate the number of distinct elements in the stream? Any ideas?
Since the input will be like the user features, they should be of similar forms, and we can just extract part of the streams. The more parts we extract and hash into a bucket, the more accurate we can achieve while the cost is higher.
Okay. Okay, I don't disagree that the more information we can save and extract, the accuracy should go up. Yeah, okay, that would be certainly correlated. There will be some trade-offs. The more space, the more accuracy we get. Maybe one thing I'll suggest is that, for example, in extreme cases where, okay, so the tough part is that items can repeat, right? You get like a new element, and then just the same one repeats forever, and then like a little new element shows up, and the same one repeats forever. A new element shows up and then the boring one repeats forever. So if you're doing like a random sample where you take some of them, because your unique, the distinct things that only show up like once or twice is just completely swamped by the chat bot that keeps showing up, or not chat bot, the search engine bot, the spider that dominates your logs. You won't even sample the interesting, distinct IDs. Okay. Maybe any other ideas? Yeah. Okay, so okay, can we do something like heavy hitters? Okay, so if I allocate some array of size W, okay, and then I guess we're hoping that, well, okay, so what would actually happen? Let's say there are more than W distinct elements out there, much more. Then first of all, you're probably going to get some non-zero tallies in every cell. Might be more, might be less, and stuff like that. And I don't even know if we can distinguish between, okay, so if there was like W squared distinct elements, then I think with pretty good probability we'll hit every cell. So every cell will be non-empty and we'll get positive tallies. And then if there was an infinite number of distinct elements, of course we would also fill up all the cells. So I don't quite see how we can distinguish between even w squared, where w for us was like epsilon or something, so it's very small, and arbitrarily large numbers. Well, sure, but remember, one thing is that before we would choose the threshold for heavy hitters, and then we chose w proportionately. But here I'm saying that once you decide you're going to use some fixed amount of space, uh, I'll have w squared, really big things that'll swamp the squares. Let me point out one maybe soft difference, or one thing that's sort of odd. So in our heavy hitters data structure, every time an element came in, we updated the state of our algorithm, right? We increased some tally. That's clear. But if I'm interested in distinct elements problem, I see 5 new elements or something, okay, I should probably be making changes because the answer is changing. That makes sense, right? But now suppose 6 through a gazillion are all just the same element over and over again. At some level, the number of distinct elements hasn't changed. And so really the state of the problem hasn't really changed, but our data structure is going to be doing lots of work, right? So our data structure is sort of out of tune, out of sync, because it's always flipping some bits, even though the number of distinct elements is not changing. That's one thing that's sort of off. That's not a formal argument of anything, but yeah.
For this problem, are we assuming any property of the string? For example, like you mentioned in the website, typically the majority of the elements are repeated.
No, this is an algorithms class. So we're going to do worst case analysis, and we're not going to cheat. Yeah. Yeah. No, I'm not going to assume anything. Yeah.
You can try having like using multiple hash functions, and so like for a given element, you can tell if it's appeared in the string before, if it like hash across multiple functions has appeared. So since you can like just increase the number of hash functions, like you can more uniquely identify it. If that makes sense. Versus just having one.
Okay. Can we kind of save the hash? Maybe you're thinking of a Bloom filter? No? No. Well, let's see. I feel like at the end of the day, you're implicitly trying to sort of still save the names of things you've seen.
Actually, we do not have to do it with this algorithm. We can prepare multiple arrays with multiple hash functions, and when we allocate, we will hash an element to each element will run all the hash functions and allocate them to each arrays. And if there is if an element is hit to another element in the same bucket in every array, we can identify them as the same element in this case.
So one thing to keep in mind is that our space usage, where'd it go? Our space usage is supposed to be very small. Oh, it was there the whole time? Sorry. Our space usage is supposed to be very small compared to the length of the stream, compared to the number of distinct elements and stuff like that. So any of this kind of, let's hash something here and roughly save the name somewhere.
We do not need to save the name. We just save the number of counters, the number of elements that is hashed into this.
Okay, so but at a high level, you're just saying let's make W bigger or let's make more copies of W.
Yeah, exactly.
So let's say you make something that works for 1,000 elements. Now, what happens if you wanted to make it work for 1,000,000 elements? Would you have to make it proportionately bigger?
The advantage of this algorithm is that we can linearly increase the space while exponentially decrease our error probability.
So I'm saying that no matter what you fix, once you fix a certain number of arrays, maybe arranged in clever two-dimensional, however many ways, but it'll be finite. Maybe it'll be W over epsilon, right? It'll be W times log n or W squared or whatever. I'm just going to make the number of distinct elements that squared or something and still swamp you, which is much bigger than your data structure, but much smaller than, the potential length of a stream. Yeah.
Could you maybe do heavy hitters, and then if something isn't a heavy hitter, correct heavy hitter at any time you did something new and increase the counter as large amount of them will
Okay. Well, first of all, you're screwed as soon as you use the word probably, but okay. So let's say you pick some epsilon, I don't know, 10% to be heavy hitters or something, and then you're saying, okay, whenever I find something that isn't a 10% heavy hitter, then I'll just assume it's brand new, right? So first of all, the stream might not have any 10% heavy hitters. It might have a lot of 5% heavy hitters. Wherever you draw the line, it could be right underneath. But in general, you're not distinguishing 5% from 0.001%, right? Or things that only appear once versus things that appear a constant fraction of the time, which is really a big difference, yeah?
Why you dismiss the random sampling idea? Like, couldn't we randomly sample a portion of the stream and then count the number of
Sure.
elements in that stream and now extrapolate that to the
So, okay, so how big do you want your random sample to be?
like a constant value, say like
5% of the stream or something, right? Okay, so let's say you want to sample 5%, which by the way would be still huge because you're doing a linear fraction of the. But I'll still give you 5% just for fun, so just be generous, okay? And let's say there's 1,000 distinct elements, okay? So if I just take 1,000 and multiply it by much more than 1 divided by 5%, so I just did 10, 100, billion, gajillion thingies, your 5% will not contain any of the 1,000 distinct elements. There's high probability. You only get the one element that repeats over and over again. So let's say there's 999 distinct elements that each appear once, and then one element that otherwise dominates the whole stream. It's very hard to sample and pick it out. Yeah. But can I give you guys a hint so that we make a little more progress? Okay. All right. Okay. So here's also a hash, but slightly different than we've done before. Okay. So suppose I give you a hash function that for each element assigns a unique real value between 0 and 1. Essentially a unique ID. Okay, but it's distributed uniformly at random between 0 and 1. Okay, so the average will be 5.5 and stuff like that. Or let me give one more hint then. All right, suppose I gave you the following fact. This is just a mathematical fact. Suppose you had k independent random variables that are uniformly distributed between 0 and 1. Okay, y1 through yk, they're all just these fractional values. Independent, uniformly at random. And let's look at the minimum of the k. I'm telling you that the expected value, the minimum of k of these values is 1 over k plus 1.
raise that value to the power of -1, then don't we roughly have
Yeah, okay, so yeah, try to figure out what is the correspondence here. Yeah, what are you trying to do? Give me an algorithm. It is true that 1 over k plus 1 flipped upside down gives you something close to k, yeah?
So we take the true minimum value of y1 to yk and then flip that and use that as k.
Okay, but let's now just semantically match, I think, what you have in mind to the original problem distinct elements. So you have a stream coming in. You want to estimate the number of distinct elements. You have a few math tricks. What's the algorithm?
For each element that comes in, you hash the element using the hash function we have. So it gives you about 0 and 1. You also keep track of the current min. If a new element came in and the hash is lower than the min, you update the min with the hash value of the incoming element.
Okay. So let's try to keep, for each element, let's track the minimum hash, where the hash is some number between 0 and 1. Okay. That means what is the so x is just keeping track of the min. It initially starts at 1 because it's the biggest possible. Otherwise it keeps replacing with the min. All right. So what is the expected value of x? A high level.
1 over k plus 1, where k is the number of distinct elements.
All right. Good. All right. So it's 1 over k plus 1, where k is the number of distinct elements. Okay. So x actually reflects the number of distinct elements. And what's great, right, is that if the same element repeats over and over and over again, your min doesn't change. So you kind of pass that sanity check. The state doesn't change when the distinct element isn't changing. All right. And then what would I return? Well, you don't know the expectation, but you know x. So we'll return 1 over x minus 1. Okay, so that's the algorithm we'll analyze. Okay. All right. Okay, so in general, what is the expected value? I mean, it's reasonable to ask, what is the expected value of what we return? Right? And what is this? Actually, it's not k. It's some huge mess. Okay, so if you actually worked out the math, it gets to be a big issue because x is in the denominator and it actually blows up. So the expectation is actually not very well behaved. But that's okay. What I'm really interested in is what are the odds? So we're going to let k denote the number of distinct elements from now on. What I'm really interested in is what are the odds that what I return is close to the right answer? Roughly k. Okay, so that's our first lemma. Let's let epsilon be small. It says that if x is close to its expectation, so x should be 1 over k plus 1. And if it's saying that, oh, if x is between 1 minus epsilon over k plus 1 and 1 plus epsilon over k plus 1, then the thing we return will be pretty close to k. Goes up to 3 epsilon, but that's no big deal. We can just make epsilon smaller. Okay. So yeah, we're not going to worry too much about the expected value of 1 over x. We're just going to worry about when is it accurate. Okay, in fact, we'll go, yeah. Okay, so how do we do this? Okay, this is actually not so creative. We just kind of start flipping things upside down and just work through it. So this is if and only if. Here I'm just flipping things upside down. The inequalities get flipped, which is a mistake I always make. Okay, so I just took the reciprocal of everything. Okay, and then as long as epsilon is Okay, so as epsilon goes to 0, 1 plus epsilon is pretty close to 1 minus epsilon because they both go to 1. Okay, so this is my lazy way to get around it. So for sufficiently small epsilon, I can sort of simplify the right side. Maybe I'll throw a small constant like 3 in front. That'll hold for some sufficiently small epsilon on the left-hand side. Oops. Okay. So this is a little bit of an eyesore, so this is a little easier for us to think about.
What are we using 3?
You have to give up a little bit. So 1 minus epsilon is actually a little bit, it's not exactly 1 plus epsilon. Yeah. So I just add a little bit of padding, and for sufficiently small epsilon, that'll be true. And you guys don't actually want to watch me work that out. Anyway, yeah. Okay. Thanks. All right. I just write nonsense and hope it's really the impression that matters. Okay. The truth beneath the truth. Okay. All right. So whatever. This is just dealing with the awkwardness between the fact that we have an x on one hand and we're returning 1 over x minus 1 and trying to understand when we're accurate and when we're not. It's just some calculations. All right. So what are we really interested in? Okay. So what we kind of worked out is that when x is very close to its average, then we'll get a good estimate, right? So we want to show that x is close to its average with good probability, right? All right. So let's analyze this quantity. Any ideas? Chernoff. So Chernoff is useful for independent sums, which is not what we have here. Yeah. Oh, true. That wasn't quite the direction I had in mind, but that's not a bad idea. But I don't think it'll actually work. But does that mean? Okay. So one thing. Do you guys like having the door open? Oh. Oh. Okay. Fine. I know. Fine. So thank you very much. Um. Okay. I was hoping somebody would say Markov's inequality. Like that. That's okay. All right. So. Uh. Okay, so normally I put it in numerator, but here I just flipped it upside down. Okay, so Markov's inequality gives us that. That's it. Now, how do we analyze this? Yeah, it doesn't apply. So why doesn't it apply? The absolute value. So the absolute value is a huge pain. It's really the moral of this exercise. This is also a big factor that's bad, but I don't really know how to work with the absolute value. And this comes up for many other problems as well. Yeah. Good. Okay, so that's the theme. Okay. So let me give you guys one more fact about the minimum of a bunch of random variables. So I've also worked this out. The expected value of the square of the minimum is 1 over k plus 1 or times k plus 2. Okay. Take that as a fact. All right, so when we want to analyze the absolute value of something, and absolute values are messy to work with, they're not really natural mathematical objects. So the desk moves. Okay, all right, so what we do in this kind of situation is we square both sides, which at the moment doesn't really seem that appealing. It will be in a moment. Okay, and we'll apply Markov's inequality to this. Okay. Okay, fine. All right, but now let's look at this term. Previously, we were faced with an absolute value. Now there's a square there. What might be the first step towards kind of unrolling this thing? Yeah, let's expand. So we can expand now, which we couldn't do before. So you get an x squared minus 2 times, well, I guess I can go slowly. So if I did everything inside of the expected value, you get that. Okay. And we can sort of, I guess it's technically linearity of expectation. I guess if I were to go more slowly, I would write this out first. Okay, so I've just separated the terms. Okay, so this looks a little ugly because we have a bunch of kind of nested expectations. Let's just work through it. So let's take this one. The expected value of x squared. All right. This simplifies to what? Yeah. Yeah, so, okay, so we have this outer expectation, but this inner expectation, once you evaluate it, is just a number now. There's no randomness left on the outside. Okay, so you just left with one expectation. Okay. This first one doesn't change, so I'll write it down. Okay. What about this funkier term in the middle? Yeah. Okay, yeah, again, the same thing. So inside, this is now just a number. It's no longer random. So you're really just looking at the average of x times a fixed number, which gets you another expected value of x. Okay, so you get something like that. Okay, this already looks cleaner at least, right? So somehow, I mean, really the main thing we did was we squared it first and that let us unroll it and life is looking better. Okay. Now we can plug in some of our facts for the expected values of x and x squared. So that's like, I guess, 2 over k plus 1 times k plus 2 minus 1 over k plus 1 squared. Does anyone want to do some quick mental math? I wrote it down, but something like that, which just is roughly 1 over k squared or some constant. Okay. All right. So I can plug that back in. So I guess the k plus 1 squares will cancel out between the blue and the purple. So I'm left with k over k plus 2 epsilon squared. Okay. All right. So at least we came up with a nice, clean, closed form. Okay. So the probability that the error is bad, the error in terms of x is bad, is at most k over k plus 2 over epsilon squared. Nice and clean. Okay. This isn't great though. Why? All right. So we showed this. Nice and clean. At least we can agree. But there's something odd about it. Think of k as being big. Think of epsilon being fairly small. This is going to be greater than 1. So k over k plus 2 will get closer and closer to 1. And 1 over epsilon squared, even for epsilon is like 1/2, is already at least 4. Okay, so unfortunately, the right-hand side is bigger than 1 for even modest values of epsilon. Okay, so I didn't quite get what we wanted. But we made some progress insofar as it looks clean and it's colorful. And now the next question for us is how to reduce the right-hand side. Okay. But before answering this question directly, let me explain what we did, because we implicitly worked with something called the variance, which you undoubtedly heard of. Okay, so the variance of a variable x is the expected value of x minus its expected value squared. Okay, so x minus expected value squared is sort of, describing the deviation, right? The absolute deviation, except the absolute values aren't nice, so we do the square instead. That's not uncommon. And that whole like expanding things out and everything canceled out nicely is exactly what we did to go from that middle definition to the right-hand side. Everything cancels out nicely. That's what we did together. Okay. And we implicitly applied Chebyshev's inequality, okay, which let me state out loud. Okay, the probability that the absolute deviation, the absolute value of x minus the expected value of x, being greater than some alpha, for some alpha you give me, is at most the variance of x over alpha squared. So it's a very similar form to Markov's inequality. Okay, but there's been some changes. How do we prove it? You guys just secretly proved it, so how do you prove it? Okay, so what's the first step, I guess? Right? And then, now we use Markov's inequality. So the expected value of x minus expected value of x squared now has a fancy name of variance over alpha squared. What's amazing is that almost everything we do in this class starts with Markov's inequality and maybe some hack that comes before it. And Markov's inequality is itself a very simple argument of, oh, you can't be 2 times bigger than the average more than half the time. I always find this remarkable. All right, so let me go back to, let me just explain what we did here. So here we actually really did Chebyshev's inequality manually, where we wrote out the squaring first. Down here we did exactly the calculation. Yeah, so I guess the only point is there was a name to the madness. All right, but let's go back to, okay. So let me restate the question of how to reduce the right-hand side. So Chebyshev's inequality says, okay, the probability of error is at most the variance times this factor, okay, where the variance is roughly 1 over k squared. And now my question of how to reduce the right-hand side, I want to think of it as how do I reduce the variance of x. All right, so that's the next question for you guys. Okay, so we have an algorithm that's not quite good enough because actually our bound is usually bigger than 1. But if I can somehow find a way to reduce the variance of my experiment, so to speak, and I can drive the right-hand side down to something more interesting, less than 1, then we're very close to done. Okay. All right, so the high level makes sense. So we have an experiment that gives us x. It's kind of okay, not quite good enough. I want to, in particular, reduce the variance. The variance is too high. The ideas. Sure. Okay, so the suggestion was we can use multiple hash functions and aggregate the results to drive down the variance. Okay, so let's just expand on that. Okay, so we have whatever 20 or 100 hash functions, and we can get the hashes of each, and maybe you get 20 or 100 minimums, right, from independent copies. The next question, though, is aggregate. So how might we aggregate? We do want to, yes, take lots of more information and combine it and hopefully get a better answer. But there's many ways to go about that. Average. Okay, average is a very natural thing. So we'll just do a lot of independent trials and take the average of the outcomes. We can use the what? We can use the median. The median. The only issue, though, is that right now we have an x that's like basically never correct. So the median is also never correct. But we can look at the average. All right, so how do we reduce the variance in general? We're going to take the average. Okay, so I'm letting x1 to xl be independent copies of the same experiment. And I'm using bar x to note the average. All right, so the goal was to reduce the variance of x. So let's try to calculate that. So this is right now just plugging in the definition of variance. Okay, so the variance was x minus expected value of x squared. So for us, we had a 1 over L in front, so that dropped out to become 1 over L squared from the x minus expected. Here I've expanded out x into the sum, and I've already applied linear of expectation to the expected value. Okay, so this is maybe one step into the definition. Okay, all right. So this comes out to, I guess, 1 over L squared times, we can expand out this crazy thing. Okay, so I'm imagining expanding out the polynomial and then applying linear of expectation. I guess I could have. So tell me if this goes, if I'm skipping a step, or if I should explain this, because I could have written out one more line in between. Okay, so here I was just expanding out the polynomial and applying linear to the expectation. All right, so this is still a bit of a mess. Okay, what does this become?
they are independent, right?
The xi's are independent. That's very important. Yeah.
The expected value of the product is just the product of the expected value.
In particular, when okay, so all right, so let's look at this. We have two cases. If I is not equal to j, do I have space? You can make space. Okay. So when they're different variables, this expectation of the product can be broken up into the product of expectations. We can split them apart. Okay. That's all I intended to do there. And what is that? Variance of xi times variance of xj. That's a reasonable answer. Any other ideas? Variance has a square. Yeah. 0. The average of x minus its average is 0. Okay, so these all go to 0. That's great. We've got rid of most of the terms. What happens if I is equal to j? Yeah, so this would have been xi minus squared, which is the variance. Okay, so all we're left is the variance of the along the diagonal. And they all have the same variance as x originally. So get 1 over L squared times L of the variance of x. And of course, a pair of L's cancel out. You may have done this in a probability class before. But the point is, if I make 100 copies of the same experiment, the variance is going to go down by a factor of exactly 100. Great. So let's go back to, then our suggestion was, okay, we have something that's variance is too high, otherwise it's kind of okay. So let's make L independent copies of x. I'll let x bar denote the average like we just did on the previous slide. And now the variance of x bar is equal to, sorry? Yeah, which is, okay, so 1 over L times, I guess, 2k over k plus 1 squared times k plus 2. Something like that. Okay, and if we now do the same thing we were just trying to do, but with x bar instead of x, the average of L instead of x, Chebyshev's inequality would give us this. Okay, and plugging in what's right above it, some k plus 1s cancel out. We'll get like 1 over L times, somehow a 2s snuck in. Well, let's pretend it's not there. Doesn't matter anyway. Okay, same thing as before, but now it's gone down by a factor of L. L is under our control. Okay, so in particular, if I wanted my probability of error to be at most delta for some parameter delta, what should I make L? Yeah, but by sigma, I think you meant epsilon squared. Is this what people got? Just a sanity check, you're saying that for smaller probability error, you need fewer samples or independent copies. Okay, the delta's on the other side. Yeah. Okay. Okay. So in particular, you get constant probability of error was 1 over epsilon squared space. So here we took averages to reduce variance, and that made Chebyshev's inequality more effective. Okay. Good. Good. All right. So what can we do next? All right. So I have something that works a constant fraction of the time for any constant I want. It can be 90% of the time. Get an A minus. But none of you guys are ever happy with an A minus, right? You want an A plus plus. So how can I get this to really high probability? Right now we get this delta dependence, which I made the same mistake. Okay. Right now we get this delta dependence. So if I wanted to be like 1 over polynomial error, I would have to use polynomial space. I would now like to get 1 over polynomial error using logarithmic space. Okay, so this is the big conceptual question. It doesn't just apply here. I have something that's accurate 90% of the time. How did I get that up to 99.9999999% of the time? Yeah? Okay, you can run it multiple times. Okay, so let's say you run it multiple times. Then what? You now have multiple things running. It will involve running it more, yes. We can take the average. But I think that's just going to have the same effect as this. You're just going to end up reducing the variance because an average of 10 groups of 10 each is just the average of 100.
The average, we need it to be in the form where the final answer will be wrong only if every instance is wrong. Then we reduce constant error to polynomial error.
Yeah, so if we think of heavy hitters, for example, the way we were able to get super low error was because we had gotten to a situation where everything had to be wrong for that data structure to be wrong. So it was like, oh, the odds of getting 100 straight tails is 1 over 2 to the 100, right? So, but well, in this case, suppose you ran 100 copies and one of them was correct. That would be the equivalent with heavy hitters. What good is that for you? How would you be able to figure it out? So you've run 100 of them, and I tell you one of them is correct.
Plus minus epsilon is making things more complicated because if we know the error is one directional, like it's always 1 plus epsilon or 1 minus epsilon, we can just take either the thing or the math.
Yeah, so the great thing about heavy hitters is that we had one-sided error, and that's what made it so easy to amplify. In fact, that's why it's in lecture 2, because it's so clean. That's not the case here. Our estimator may be too big, our estimator may be too small. Okay. So, right, so my warm-up was, okay, you guys remember all these questions, right? And about how, things get very concentrated close to the average, especially with a large trial. The fancy name, well, one fancy name is concentration phenomena. The other fancy name is the Chernoff bound. Okay, so how do we apply the Chernoff bound here? Okay, all right, so it's not the mean, it's not the min, it's not the mode. You guys remember the mode of a distribution? It's like the most useless thing in the world. I don't know why it exists. Okay, so we're going to make some number of copies of something that, let's say it's correct 90% of the time. Okay, and rather than returning the mean, we're going to return the median. Okay. So why median? What's the logic? What has to go wrong for the median to go wrong? So you run 100 copies, and you're going to order them. Right?
More than half of them will have to be a terribly small underestimate or overestimate.
Yeah, so, okay, so you have, how do I do this? Okay, so you have a bunch of estimates that are right or wrong. And you don't know what the right answer, of course, is. But you're going to pick the middle one, which hopefully is that one. But I'm not sure. Okay. So if this is too big, then all of these are too big and wrong. If this is too small, then all of these are too small. So if this is wrong, at least half of them are wrong. Okay. Okay. And it succeeds if at least half of them are correct. How many of these are in each means? How many of these means do we expect to be correct? Yeah, and for us, what would that large constant fraction be? So let's let z be the number of yi's that are correct. What is the expected value of z? So I'm assuming yi's have 10% error. All right, 0.9q. At some point when I was writing the notes, I realized that q and 9 are the only combination of letter and number that looks the exact same. Okay? All right, so you're expecting 0.9q to be correct, and you need at least half of q to be correct. How can I argue that's going to happen with really good odds, especially for large q or moderately large q? Okay, Markov's inequality. So okay, so we want to bound the probability that z is less than or equal to 0.5q. So that looks a little bit but the main issue about Markov's inequality is that you're not going to get the exponential you're looking for. You want something stronger, yeah. Chernoff bound. Why can we use a Chernoff bound? Yeah, so I'm going to write this as 1 minus, I guess, 4 ninths. Oh, 1 second. 9 over 10 times x is equal to 1/2. So that means x is 9/5. Did I do it right? No, 5/9. Okay. All right, so I'll write 1 minus 4/9 times expected value of z. That's I'm just putting it in the form we're more used to for Markov's inequality. Okay, so this is really 0.5q. Right? Okay, so 1 minus epsilon mu is less than or equal to e to the negative epsilon squared mu over 2. I'm not sure if that's big enough to be seen. We'll plug that in. Less than equal to e to the negative. Epsilon squared for us is 5 over 9 squared. Expected value of z is 9/10 q all over 2. I don't really care that much about the constant anyway. If I want this to be less than equal to delta for some given delta, then what should q be? Log delta? That's a negative number. Log 1 over delta. The reason it needs to be 1 over is because there is a negative sign in that Chernoff bound. That'll flip it over. Okay, and then put a big enough constant to get rid of all these annoying fractions in front. Okay, great. What's going on here? All right, so this is a very nice and cute high-level idea that goes far beyond just the distinct elements problem, right? We have some kind of approximation algorithm, and a high level, kind of our estimate wasn't even right ever, but by reducing the variance by taking the mean, we can at least get it to be right some constant fraction of the time. And then we take the median to then ramp things up exponentially. And then we get these very, very strong bounds. Okay. There's something sort of curious. About, or okay, so at a high level, you get these bounds. There's something sort of curious about our algorithm. So the expected value of the output of our algorithm is actually not at all necessarily the distinct elements. We never even analyzed that. We never analyzed the expected value of 1 over x minus 1. What we just focused on was, what are the odds that it's within a close band of the desired output? Okay. So in other words, we are outputting a biased estimator, not an unbiased estimator. This is a biased algorithm. It does not, on average, produce exactly the number of distinct elements. Okay. But we don't really care. We're interested in reliability. We're interested in robustness. Okay. What is most important is that you're accurate in some reasonable way all the time. Okay. As a general principle, that's true of many instruments, all on the ceiling and stuff like that. Okay, so instead of just trying to be like ideally perfect, just be pretty good all the time. It's a good approach to life as well. Okay, but this is an important design principle. The idea of not actually trying to design unbiased estimators, allowing a little bit of bias, but in exchange for good engineering trade-offs.
I suppose it would be more robust if we take the average of the middle elements.
The average of the middle elements. I mean, I guess you can take this and, I don't know, take more means and more medians and more expectations, but I don't think you're going to get a big win. The median trick is enough to get this exponential thing, and you're not going to get much better. You're not going to get a doubly exponential or something like that. Okay, so, but it's a very cute, simple idea that's very effective. So good to keep an eye out for. All right, so I thought we'd have time to finally do the proof of the famous multiplicative Chernoff bound. Okay, and maybe I'm not too concerned with, well, maybe I am concerned. Well, let's just do it, okay, because we've been putting it off for long enough. All right, so here then is, I might not get the best constants in the world. I'll just do whatever I can think of off the top of my head. But at a high level, let's show that if I have n independent random variables and use the average and there's some epsilon, the odds of deviating from the average is exponentially small in the average times some epsilon squared. Okay. All right. So, I think I'm going to do it a little bit different that I find a little easier. I'm just going to add an extra beta there, and you could think of beta as being another epsilon mu or something. Not a big deal, but okay. I'm going to prove that statement. So for some beta greater than 0, it's just going to clean up some calculations. But the constant will be a little weaker. Doesn't matter. All right, so you guys might actually be able to guess how to start. We actually are going to apply Markov's inequality. If we apply Markov's inequality directly, we won't get anything stronger than Markov's, of course. So, as usual, we're going to try to put this on steroids, okay? Which we've done before. We have taken the left-hand side and we squared it. We did that just now. In linear probing, we took it to the 4th power. You might get the sense that higher powers might give you higher, better results. What is sort of the extreme? I guess n is an extreme, yeah. Well, another extreme is just an exponential. Okay. So if the left-hand side was bigger than the right-hand side, then e to the left-hand side is also bigger than e to the right-hand side because e preserves order. Bigger numbers go to bigger numbers. Okay. Now we apply Markov's inequality. Somehow everything comes down to Markov's inequality, which is a very elementary argument. I'm going to do something else though. I'm going to put a little parameter t here that we're going to use to kind of fine tune at the end. Okay, so let's let t be some parameter greater than 0 to be determined later. Making t bigger kind of exaggerates the exponential, making t smaller kind of dampens it. Okay. Put some t's in there. This looks messy, but we're actually almost done. Rats. Something like this. Okay. All right, so let's focus on this. That's really the only thing left to analyze. Okay. Okay, this is some exponential to the sum of stuff that seems difficult to analyze. How can I break this up? Okay, so the reason, well, big reason why we like the exponential is because it lets us break up the sum easily. It's much less painful than like expanding out polynomials. Okay. Now let's look at one of these. All right. This is sort of pain. Expected value of e to the txi. Okay. All right, so let's assume that t is less than 1. How do I deal with this? In 1 minute? Okay. e to the x less than or equal to 1 plus x squared, as long as x is, say, at most 1. One plus txi plus t squared xi squared. Okay. Now xi was between 0 and 1, so to make our life a little easier, I can just drop one of these squares. That's okay. That's only going to make it bigger. Okay. All right. But the nice thing is that this is very easy to compute. 1 plus t squared, expected value of x to the I, x sub I. Okay. I want to plug this back in up above where everything is exponential again. So how can I turn this into exponential something? We'll use the other one. Okay. So what's kind of going on here is that for x very small, e to the x is very close to 1 plus x. And remember, the general context is I'm looking at very small numbers adding up to something big. So x is small. Okay. So we're able to kind of toggle between e to the tx and then bring it back down to do an easy calculation and bring it back up. And we're not losing too much because at a high level, e to the x is roughly 1 plus x at this scale. T plus t squared, expected value of xi. Okay. If I plug that into here and I add them all up, this product will become t plus t squared, and then you'll end up with a sum. The sum of expected values, right? So we do this for all the i's, we lift it back up, and they add up in the exponent. The sum of expected values is mu. Okay. All right. And we bring back from before e to the negative t, 1 plus epsilon mu plus t times beta, where beta we get to choose. Okay. What would be a convenient choice of t to make some of my terms disappear? 1. Wrong answer. Also wrong. Also epsilon. Great. All right, so then we get epsilon plus epsilon squared on one side, and then this will also be epsilon plus epsilon squared. Okay, so those mu terms cancel out, and I'm just left with, there should be a negative sign, e to the negative t beta. Okay, so things there cancel out. If we go all the way back to the top, if I, for example, choose beta to be epsilon times mu, okay, then this is, and t was chosen to be epsilon, I get e to the negative epsilon squared mu. Okay, that's what we wanted. So just to remind us, what we really showed directly is greater than 1 plus epsilon mu plus another epsilon mu, that was beta, is less than or equal to e to the negative epsilon squared mu. So if you wanted 1 plus epsilon mu instead of 1 plus 2 epsilon mu, you just divide things by 2, and then you end up with a factor of 4 on the right-hand side. Instead of 3, this is a little weaker, but this is obviously clean. Okay? All right, so that was the proof, but I think the high-level idea, though, is that we're putting Markov's inequality on steroids and taking advantage of the fact, at a high level, why is it that many little pieces, when adding up to a big average, is so strongly correlated? It seems like part of it has to do with the fact that if those x's are small, these basic approximations that e to the x is roughly 1 plus x, we're not losing very much. That seems to be what's going on at a high level. All right, thank you.